Hi everyone, myself Satvik, roll number 20951A05G4, branch CSC section C. The topic which I got for TED Talk for the subject operating systems is file system workload on a scientific multiprocessor. Introduction. Many scientific applications have intense computational and I/O requirements. Although multiprocessors have permitted astounding increases in computational performance, the formidable IO needs of this UO needs of these applications cannot be met by current multiprocessors and their IO subsystems. To prevent IO subsystems from forever bottlenecking multiprocessors and limiting the range of feasible applications, new IO systems must be designed. The successful design of computer systems, both hardware and software, depends on a thorough understanding of their in, intended use. A systems designer optimizes the policies and mechanisms for the cases expected to be most common in the user's workload. In the case of multiprocess file systems, however, designers have been forced to build file systems based on a speculation about how they would be used, extrapolating from file systems characterizations of general purpose workloads or uniprocessed and distributed systems or scientific workloads on vector supercomputers. To help these system designers, in June 1993, we began the Charisma project, so named because the project sought to characterize I/O in scientific multiprocessor applications from a variety of production parallel computing platforms and sites. Methods. To be useful to a system designer, a workload characterization must be based on a realistic workload, similar to what is expected of it in the future. This means that we had to trace a multiprocessor file system that was in use for production scientific computing. The Intel IPSC or 860 at NASA Ames Numeric Aerodynamic Simulation Facility met this criterion. The facility's three newer multiprocessors, an Intel Paragon, a thinking machine, and an IBM. Ideally, a workload characterization is an architecture independent representation of the work generated by a group of users in a particular type of computing environment. However, since the architects of different parallel IO subsystems are so diverse, any observed workload will be tied to a particular machine. While we have tried to factor out these effects as much as possible, some care should be taken in generalizing our results. Data collection. For our study, one trans file was collected for the entire file system. We traced only the UO that involved the concurrent file system. We did not record any IO that was done through standard input and output or to the host file system, all limited to sequential Ethernet speeds. We collected data for about 156 hours over a period of 3 weeks. While we did not trace continuously for the whole 3 weeks, we tried to get a realistic picture of the whole workload by tracing at different times of the day and of the week, including nights and weekends. The period covered by a single trace file ranges from 30 minutes to 22 hours. The longest continuous traced period was about 62.5 hours. Tracing was usually initiated when the machine was idle. For those few cases in which a job was run, running, running when we began tracing, the job was not traced. Tracing was stopped in one of the two ways, manually or by a system crash. The machine was usually idle when a trace was manually stopped. The trace files begin with a header record containing enough information to make the file self-destructive and continue with a series of event records one per event. These events include individual read and write requests as well as operations like file extension and deletions. Results. We characterize the workload from the top down, beginning with the number of jobs in the machine and the number of users of files by all jobs. We then examine in individual IO requests by looking for sequential regularity and sharing in the access pattern. Finally, we evaluate the effect on caching through trace-driven simulation. IO request sizes. We show that the vast majority of reads are small, but the most bytes are transformed through large reads. Indeed, 96.1% of all reads were for fewer than 4,000 bytes. But those reads transferred only 2% of all data read. Similarly, 89.4% of all writers were for fewer than 4,000 bytes. But those writes transferred only 3% of all data written. The number of small requests is surprising due to the poor performance in CFS. The jump at 4K bytes indicates that some users have optimized for the file system block size. But it appears that most users prefer ease of programming over performance. The figure shows spikes in the number of small requests as well as in the data transferred by FM bytes requests. While the spikes of small requests occur throughout the tracing period, one trace alone, probably one job alone, contributed the spike at 1 M byte. Although the specific position of the spikes is likely due to the effect of individual applications, we believe that the preponderance of small request sizes is the natural result of parallelization by distributing file data across many processes and would be found in other workloads using a similar file system interface. IO request interface. We define the number of bytes skipped to be the interval me. Consecutive access have interval size 0. The number of different interval sizes used in each file across all nodes that access that file is shown in a surprising number of files were read or written in one request per node. Over 99% of the first interval files were consecutive access. The remainder of one interval sizes files, along with the two interval size files, represent 5% of all files and indicate another form of highly regular access pattern. Only 1.2% of all files had three or more different interval sizes, and their regularity was more complex. To get a better feel for this regularity, we also counted the number of different request sizes used in each file. More than 90% of the files were accessed with only one or two request sizes. Combining the regularity of request sizes with the regularity of interval sizes, many applications clearly use regular structured access patterns. Conclusion. Although this workload had many characteristics in common with those in previous studies of scientific application uh, and file systems, parallelism had a significant effect on some workload characteristics and added some new characteristics. A multiprocessor used for scientific applications will not be well served by a file system ported from a distributed system, which was tuned for a different set of workload characteristics. In particular, parallelism leads to new interleaved access patterns with no temporal locality and high inter-process spatial locality at the IO node. Compute node caches are probably best implemented as a single buffer per file, but only if carefully managed for consistency. IO node caches can effectively combine small requests from many compute nodes, avoiding extraneous disk IO and raising the potential for large disk IOs. A significant benefit when the IO nodes serve reductant disk arrays rather than the individual disk replacement policies other than the least recently used. With this, we have come to the end of the topic. Thank you.